Just a reminder, next Tuesday we'll do the mock midterm. All it is, it doesn't count towards any of your grades. It just gives you an opportunity to look at something that looks like it could be an exam. Okay, it will have a similar format. And so I encourage you to come here. You'll just get it. You can fill it out. And then on Thursday, you'll have a chance to look at the solution and to discuss it during the exercise session. Now, I know that typically, particular when it comes to the kind of more theoretical part in the exercise session, there's not a lot of hold of attendance. Just be careful. At the end, 60% of your grade is on the exam, right, and not on the project. So it might be a good idea to, so far most of it was project because you need to get up to speed, you need to think about it. But at the end, what will count a lot will be the way how you do it in the final exam. And so it might be good to now think about also put some effort into this. So what is the plan for today? I want to spend maybe 10 more minutes to repeat or to summarize what we have talked about last time, namely talking about the kernel trick. It should be clear that we presented it here in terms of least square ridge regression, but of course, this kernel trick is a much more general idea, and you will encounter it in many, many other applications too. This is just an example. And once we have done with this, we'll go to the next set of techniques, and they all will have to do with unsupervised learning. So far, everything had to do with supervised learning. You got samples. The samples were feature vectors and labels, either zeros and ones if we're talking about classification, or just numbers if we're talking about regression. And so this is like someone telling you for every, let's say, picture, whether that's a cat or dog. So that's why it's called supervised learning, because you have like a teacher there or a supervisor that tells you for some examples what it is, so that then later on you can apply this to examples you haven't seen. But there's another area which is called unsupervised learning, which the only thing you get are just feature vectors. And you're not told, you're not told the labels or whatever other task there is. And so this is maybe less evident in the beginning how you could possibly learn anything. And so what we will do today is to start doing an overview, kind of like what we had done for the area of classification. So I'll just tell you maybe for an hour just various techniques, whatever, matrix factorization and many other techniques that you have. And then we'll start, and about each of these topics, you'll have at least one full lecture, some maybe even more than that, that explain these things in detail. And probably we get started with this today, and particular on what's called k-means. Okay, so that's the plan. So let's go back and let's summarize so the kernel trick. And we had done it in the context of ridge regression. And of course, ridge regression is just least square with a regularization term. And so let us summarize what it was. Well, the ridge regression itself, right, the cost function was that we wanted to minimize the sum of all these terms, so yn minus some model x and t w squared so this is what we wanted to minimize, and we learned that an optimum solution for this vector w can be written down in various ways. One is if xt is this data matrix, right? So capital X is the n by d data matrix, which has xn as its rows. And so then this is transposed xt times x plus lambda. This was of dimension d, and then minus 1 times xt times y, and y was the set of all the labels. So this was one way to do it. And we also learned that there's another way to write it. We can also write it as xt times x xt plus lambda I n times y. And we had called this thing here alpha star. Right? So there were two ways to write this solution. And so we said that if we first just the learning task itself, right? So this was here, what was the computation here? So this was something like nd. So here the thing was something like d third. Why was it d third? Because this matrix here is of dimension d by t. This is d third plus n d squared complexity. And this, just computing that, was n third, the inverse. So I have again here the -1 missing. So the inverse plus d times n squared. So these were the two complexities, right? So this was just to learn. This was the learning part. And then, of course, we still had the prediction part, right? And so the prediction part was then that for a new sample, we get, maybe let me just write tilde because we have lots of x's and xn around, and so this is now just one new sample. So let me just write tilde. So then for the new sample, of course, if this is a new sample here, then the prediction part, right, will be like this. And so again, of course, this can be written in various forms. It can be written like this or like this. And then for this W star, I can put this in there, right? I can also write it as X transposed times the alpha star, right? That's another way of writing it down. And so just let me write this down here, what this is explicitly, right? So this goes over all samples. N is 1 to n of the X tilde t, the x n, right? So the inner product of the nth sample with the new sample I have, and then I multiply this with the alpha star n. Right? So these are the two ways how I can make the prediction. And so this is obvious, right? We always take this W star. I just take the inner product. That is my prediction always. This is just another way of writing this W star. And we'll see in a second why I want to write it in this more complicated form. This looks clearly more complicated because this was just one inner product across the data here, right? This is just a vector of length d, versus here I have a whole sum over n, and I have many inner products. And so right now this seems quite stupid to write it this way, but we'll get back to it in a second. Okay, so far there was really nothing. And now we come to the idea of the kernel. And so to the idea of the kernel, there were basically two alternatives, right? So let's assume I go from the x, n, now to something much larger, phi of xn. And perhaps this lives in some dimension rd, and this lives in some dimension, let's say, rd whatever prime, right? And presumably, d prime will be much larger than d, right? So I'll go to a much larger feature vector. And so now I can, of course, do exactly the same, right? So now I could do exactly the same. But now all these things here will be, all I have to do, easy to do on the board, right? So all I have to do is now put everywhere here the phi around, right? Whatever, it doesn't matter. Okay. And so everywhere there will be now phis around, right? So it means I'm always working in this larger space. And so also here, of course, right? So I can now, when I predict, I can either take the phi right, so that's one way. And the same thing also here, I have phis. So let me write this again, maybe. Let me write it larger. So in the prediction part, now with this going to this larger kernel, so the y, I can either predict it as phi applied to this expanded and take the inner product with this. But this is also the same as expand it. Take the inner product with all the expanded samples, right? And then multiply by the alpha n star, right? That's another way of doing this. Okay, so, if this is much, much larger, right? We have seen, sometimes you might go to something much larger, then, so a priori, depending on the d or d prime that you have, one of these might be preferable, right? But in particular now, if this is much larger, right, if we're really in this domain where this is much larger than this, then we saw that an alternative, as long as the kernel is reasonable and or has fulfilled certain condition, right? So this is feature extension. And so we saw that alternatively, rather than going everywhere up here, right, we don't have to do this, but we have seen in here that if I look at the alpha star, so alternatively, via this kernel trick, what I can also do is, right, I know that the alpha star was equal to whatever I have here, right? So it's equal to the phi of x times phi of x transposed, right? And plus lambda n I minus 1. And then I have also the prediction, right? I could have y twiddle is equal to, let's write it down like this. Let's write it copied here. It's phi of this new feature transpose times the phi of the various samples times alpha n star. Right, so alternatively, by the kernel trick, this thing here was the kernel. And so rather than, this will still be an n by n kernel. So this doesn't change. This doesn't depend on the d. Will still be n by n. It's independent of the d of the feature space, even if the feature space is extremely large. But we said that we can compute this one here, right, the kernel, k, is equal to this phi of x times phi of x transposed, that this can also be computed in the following way. Kij is equal to this kernel map, assuming there exists one to it, of xi times xj. Right? So alternatively, rather than going first mapping into this large space, then taking the inner product, we can just apply this kernel map to the samples themselves, and then the ijth entry is simply the kernel map applied to xi and xj, right? And so that could be computationally much more efficient than going into the large space, particularly if this kernel map is in such a way that this really expands the space, right? And we have seen, for example, a case where this goes to infinity, where we couldn't even do the calculation in any other way. But this is just the computation of this alpha, of this thing here, right? So, this is what we discussed last time. So we have now an efficient way, even if we expand to a very large feature map, to compute that, right? But of course, we are not interested in the alpha in itself. We're interested in, at the end, in the prediction. And for the prediction, we have to compute this, right? So in here, it still looks that we go to the large space, right? And then, still have to compute the inner product. So can we write that as a kernel too? Is it clear? So one is how to compute the optimum alpha, the alpha star, right? And so for this, we can just compute this kernel k here just in terms of this, right? Much easier. But at the end, we are not interested in the alpha star. The alpha star is just some convenient intermediate quantity. What we're interested in is in the actual prediction, the value, right? And this value is, that's why we wrote it down in this form, can be expressed like this. I want to write this also in terms of the kernel function. How can I write this in terms of the kernel function? right? Because if, let's assume for the one kernel that gave me infinity, it doesn't help if I can express the alpha, right, if I can't express the actual prediction in the small space. So how can I write this? It's very easy, not a trick question, very easy. I wrote it already there that it's obvious. But what does the kernel do? The kernel just is exactly a representation for this inner product, right? That's exactly, so this means this is nothing else, right? So this is over all samples. This is nothing else but exactly n is 1 to n, and this is exactly the inner product of this new sample that I get times all the possible samples that I had, right? Times alpha n star. So the prediction is just this. It's just a linear combination of the kernel x, right? The kernel function x applied together with all the other possible samples that I had. And now I think it's also nice to see, so this is now everything, a prediction that's written everything in this small space, and now you can see that in this small space this is no longer a linear function, right? I mean, we talked about this many times, right? I take all the predictions are linear so far that we talked about, but if I first expand, then make the prediction and then represent this back in the smaller space, right? In the small space it's not linear, right? And you see that. It's a linear combination of this alpha n here, but it's a linear combination of nonlinear functions, right? So k could be the exponential function or whatever these functions are, right? So in this small space, right, this is nonlinear in original feature space. And that's exactly where the power comes in, is that if we're choosing suitable kernels, that now, even though we're using inherently a linear technique, we can employ, or we can create nonlinear decision boundaries, in this case where we do classification, right? Even though kind of in the large space, we actually use linear techniques, right? And so also from this, once you see that that's just a linear combination of these differences, you could maybe use that if you have certain data to understand a little bit what might be suitable functions for this thing here, right? If you think that the boundary should have certain shapes, all this can do is give you some linear combination of such functions, right? So you can from that understand what are the boundary regions, for example, the regions between the two classifiers that this can potentially create. So much enthusiasm. It's amazing. I feel. Okay, so we did this all in the ridge regression context. This has nothing to do a priori with ridge regression. There are many other examples where you can write the cost function in this kernelized form. All we have used is the fact that the objective function only depended on this xt times x, right? And that we could write the solution exactly in this form, which is again a consequence of that. That's all we used, right? And we have seen already other examples where we brought it into kernelized form, right? And so in this you could do exactly the same. So this is just, it's like a trick that you can apply orthogonally to many other examples that we have seen, right? It has nothing to do a priori, it's just to do with computational efficiency, right? It doesn't give you something new. You could have just gone to the large space and done it there, right? That would have been exactly the same. It's just a trick to do this more efficiently. That's it. Any questions? No. Okay. Good. We go to our next topic. Our next topic is unsupervised learning. Good. So far, all we have done is what's called supervised learning, right? So we have always started saying we get a training set. The training set has labels or has samples. The sample consists of a feature vector. We call it xn. And then there was an output or an output label, which could either be a 0, 1 for classification or class, or could be a number, depending if we talked about regression or classification, right? And so these were your examples, right? You show a baby, whatever, 10 cars, and say, look, this is a car, this is a car, this is a car, and hopefully, okay, if the baby is smart, okay, after a while, we'll figure out, what is a car, right? But actually, human beings, if we think about, for example, cats and dogs, right? So if Google, I don't know how many 100,000 pictures they had that they labeled and then they trained the algorithm to learn it, right? Clearly, you don't have to show a baby 100,000 pictures of cats and dogs before it understands what's a cat and dog. Okay, so there are many other things going on, not just human beings, but also for how we learn, but also, tasks that we are interested in is where we either don't have the labels, right? Or we don't have a lot of labeled data, right? Why might we not have the labels? Because it costs, right? So if you want to do some learning task, well, it's maybe easy to get pictures of animals, but someone has to sit there and say, what is what, right? And that will cost you something. So it certainly is nice if we could either not need the labels at all, or at least maybe we can enhance our learning by just using also, there might be lots of unlabeled data and then maybe have a little labeled data, right? And so unsupervised learning is exactly this, where as train, all you're given is just the labels itself, right? So it's just the xn, just the features, sorry, okay? These are just the features, and you don't have the labels. Now, clearly, I guess if you haven't really thought about it, the first time you maybe think about it, you will say, how is that possible? It makes no sense, right? If I'm not told that just giving a picture, so what, right? I'm giving 1,000 pictures, okay, what is the interesting part? But there are actually quite a few techniques. And so these techniques, so what we do now is just a whirlwind tour through some of the techniques, that where you will see that you can do interesting things with unsupervised learning. And so they fall again into different categories. Some are called more what's called feature selection. Okay, so even those techniques kind of, some what's called feature selection. And some other ones fall more in the world of models or model learning, or let's see, what else do I want to see? I forgot the other name. Okay, density estimation. So there are, again, subcategories. And some of these techniques, you can use them, for various, they don't necessarily even fall into just one category of the two. So all I do is we'll just mention now a few, talk a little bit about them, and then we'll talk maybe about 6 different such models, and then we'll start, maybe the second hour or a little bit later, we'll start with one of the first one, which is called k-means. Okay, we'll start one on a particular one. So let's look at some of the possible techniques that we have. Let's see that we start with feature selection. Let's start maybe with something called matrix factorization. And again, there are many names around, and depending on how you apply it, again, there are many names. So let's give the first example, which is with something that became famous when Netflix did a competition, and it has also many other names. It's sometimes called the Netflix prom, or sometimes it's also called collaborative filtering. Now, this example here is actually still supervised, but we'll then get back to something that is unsupervised and has very much the same flavor. So this is actually probably more reasonable to say that it's supervised, but you will see then in a second and immediately how this relates to something that is unsupervised. Okay, so what was this problem about? Probably many of you have seen this. Netflix is a video streaming service in the US. They have, in their catalog, whatever, 100,000 movies. They have, I don't know how many million users. And of course, you would like to recommend movies to people. And so what they do have is some data where, let's assume these are the movies. It's a matrix. These are people. And so this is a matrix. And so let's assume for this matrix, you would have ratings. Okay, so ratings are just numbers. And whatever the scheme is, maybe the numbers are whatever, from 1 to 5, or whatever the scheme is, doesn't matter. Okay, so you have a matrix of numbers in there, and it says how much some person liked some movie, right? And of course, later on, what you would like to do is you would like to maybe figure out, so what happens is that not all the time will you have all the entries clearly. Often you have just very few entries, right? And from these entries, you would like to learn other ones, right? So maybe you know that whatever, this is maybe, whatever, Peter, right? And this is maybe some horror movie, okay? And, maybe he liked it a lot, okay? 5, and then, whatever. But a priori, you don't even know that it's a horror movie, and you don't know that it's Peter. All you see is rows and column. And so, but, maybe you want to see how would he like that movie here, okay? But you have some of the entries in this matrix in here. Okay, clear? Is it clear what the task is? You've given some of the entries in the matrix. You would like to learn how other people or some particular people might rate certain movies, or which movies might be the most popular, because that's what you want to maybe recommend to someone. Wouldn't you like to watch blah, blah, blah? Okay? Now, so forget about right now, although that's very important, is that there's some missing entries. Okay? So let's assume just this matrix is even full. Okay, it's full, there are all entries in here. Now, let's assume that what you could do is that this matrix here, I don't know what I call it in the notes, let me maybe call it M. Maybe that you can write this matrix as represented by a matrix, or approximate this by a matrix that has a very low rank. Okay, so let's assume just rank 1. So let's assume you could write it as an outer product here. So maybe let me call this here. So these were the people. Maybe they're P such thing here. And maybe these are M. Okay, so, and now maybe let me call this matrix R for ratings. And so I want to write this as an outer product, right, of two matrices. Okay, and so what should be the dimension of these two matrices, of these two vectors? So I want to write it as I want to approximate it. This will not, of course, be exact, but I want to approximate it. And let's assume I could do this exactly, just for the purpose of thinking about it. I want to approximate it as a one-dimensional matrix, right? So what would have to be these dimensions? What should be this dimension? This is P here, right? So this will be P. And this dimension, we call it M, right? Is it clear what I'm doing? Okay, so let's assume, so that's the matrix factorization problem. I'm going to try to factorize this matrix, in this case in trivial, but just in an outer product of two matrices of rank 1. So the whole thing will be a matrix of rank 1 in terms of these two things, right? And now, of course, I might completely fail. And in what sense do I want to do this? Well, I want to do this in the sense that maybe the difference, right? If I'm looking at the difference of the two matrices is small, and I can choose maybe the Frobenius norm, the sum of the squares of all the entries is small, whatever you want to choose, okay? Right now, that's not a major concern. But let's assume I could do this very well. Is there some possible meaning that we could think of these two things?
Well, you're classifying the movements.
Sorry?
You're classifying the movements.
So let's think about it. This is a vector of length p. So what could this possibly relate to? To the people, right? So it could have something to do with the people. And this is something of length m. So presumably we'll have something to do with the movies, right? And so kind of you could think in your mind that perhaps this could be simply a classification of the various types of movies, whatever, you know, horror movies, you know, like sad stories, love stories, whatever, okay? And then the kind of people, you know, grumpy people, like no movies, okay? Happy people, whatever, you know, people that have this. And then it might make sense that there's a certain, you know, simple model for, you know, which person, which group of people might like what kind of stories, right? So similar people would have similar entries in there, right? So there will be an entry here for every movie, right? And there will be an entry for every person. And you could think of that maybe similar types of movies or similar types of people might get implicitly classified in the sense that they get similar entries, right? And so, of course, you cannot just do this now with a one-by-one matrix, right? You cannot just do this with a matrix of rank, not one-by-one, rank 1. But you could do this with higher dimensional, a matrix of higher rank. And again, so you could probably give, so now this wouldn't just be numbers, but there would be vectors that characterize it, right? And so again, you could think of that these vectors have some kind of meaning, right? There will be implicitly a space created in which these vectors have meaning, and probably people that somehow are similar, right, would probably be closely related, closely clustered in the same space, right? Because if the vectors are similar, since all the ratings depends on the inner product of what they have as a vector and the movie vector, right? What does it mean a person, two people are similar? It means that they have in their ratings, they have similar ratings along the whatever row, column, whatever I pick, right? And so this means that with the vectors that correspond now to the movies, they must get always similar scores. That's what it means, right? So they better have similar vectors that represent them. Make sense? Okay, so still vague. We'll talk about you know, this matrix factorization in much more detail. But now this was kind of still supervised because I've told you, of course, some entries here, and we haven't even mentioned the problem that, of course, I don't even know all of the entries, right? I cannot just, so I have to, you know, in what sense I want to write it down, we have to be a little bit careful because in this problem, right, if you have 1 million movies and let's say, no, maybe not 1 million movies, maybe 100,000 movies and let's say 10 million users, you clearly are not going to have all the ratings, right? Not every person will rate all the movies. If you did, there wouldn't be any problem. Typically, you have a very, very small subset of these entries in there. And so what you really want is that your factorization agrees on the things you have, right? Because the rest, of course, you don't know. Clear? But that's a technical detail. Good. So this is for the for the netflix problem. But you know, this is a good segue into another problem that Martin, who is a specialist exactly on the problem, will tell you much more about it. So I'm just going to tell you the outline. And that has to do with word representation, okay? So word representation. And again, there are many things associated to it. One is called word to vec, which is says exactly what it should say, and which is the following. You know, of course, many data, a lot of the data that we have around are not just numbers, but they're text, right? We have whatever. We have transcripts of newspapers or books or descriptions and so on, right? Or maybe we have whatever, Twitter feeds or whatever, okay? Now, if you want to learn from those, then it's not super convenient to deal with words themselves because, you know, for numbers, we know we can add, we can take derivatives for functions, we can take square roots of numbers and so on. But for words, right, what are the operations that correspond to it? So wouldn't it be nice if we could somehow, in a meaningful way, translate words into objects that we can deal with? And what are the objects that we choose? The object that we choose will be that words should also be just points in some, let's say, Euclidean space. So we'll just map words to vectors, right? And if we could map words to vectors, now, of course, I can always do this, right? I can just take the alphabet, take the 26 characters, right? Somehow give numbers to them and then, you know, whatever, right? Take the word and I could make a vector out. But I would like to do it in such a way that these vectors have some, you know, somehow pertain some of the semantics, right? Some of the meaning of these words. that perhaps vectors, words that are similar might be clustered somehow together, or that there's some other operation that's preserved, right? So I would like to keep a little bit of that information in there, because if I do it in a non-meaningful way, it might be much harder than later to learn anything, right? If I can find a meaningful representation, that might be half the battle already of learning anything. And so one way to do it is basically the same idea. So let's assume you start with a dictionary. So whatever, you pick a language, you pick a dictionary, maybe it's 50,000 words, whatever it is. And so let's assume in the simplest case, you would pick a matrix which would be quite large, because it would be as large as the dictionary squared. Okay, so every entry here corresponds to a word. Here, every entry in there corresponds to a word. So it might be a 50,000 times 50,000 dictionary, right? And typically what you do beforehand is, if you deal with words, is of course you don't want to have from one word 50 versions, right? So you get rid of endings or tense or things like that. You just, you keep kind of the core of a word, because otherwise every single word might already give you 1,000 different variations of the word, and you want to keep this in a reasonable sense. Okay, so you have a dictionary, and so I have a really large matrix, and now what we want to do is essentially something very similar. We want to have a matrix here with some numbers, okay, and so the numbers will have to do with relationships between words, right? So we want the entry ij. Okay, whatever, the entry I is maybe Federer, okay, and J is, I don't know, wins, okay, and we want to have some occurrence, okay, we want to have some relationship between them, and there should be some numerical value in there, and once I have a numerical value in there, I can do exactly the same thing, right? I can do this matrix factorization, and what does matrix factorization give me? It gives me exactly, if it's not just one, if it's one by one, then every entry would just correspond to a number, but if I take matrices of rank k, if I factorize rank k, then I will get vectors of length k that represent every word, right? So that's the basic idea. So what could we pick? We need something, some metric between words, and you have some huge corpus, right? So you start with some corpus of data, whatever, okay? Pick your favorite source, all the tweets in the last whatever, okay? And or whatever, newspaper articles, whatever is your corpus, right? And now for that corpus, you would like to do it. So that can, of course, be context dependent, right? I mean, might not give you exactly the same result. So what should you pick? You want some kind of similarity measure or some relevance measure between them. You get hired at Facebook, that's your task. Mark asks you tomorrow, what have you done? Okay, you get lots of stock options or fired. What are you going to do? So what would be a reasonable similarity? I mean, there's not the right or wrong answer. People have tried many things, and that is one that works very well, but okay, I mean, it's, you have to try it out. So what could be similarity? Sorry? But we don't have, cosine is like maybe you have some inner product, and then you can define an angle between them. We don't have it. We still want to create these things. You just have a word. You have two words, and you have lots of text, right? You have Federer and wins, and now what? What is the score? 6-0. Okay, but. Okay, so that's exactly what is done here, right? So you define a context. And the context could be, let's assume these are newspaper articles, could be the whole article, could be a paragraph, could be a sentence. All these things are parameters. So you define a context. And then what you do is you go over all your sources. You look for every context. Maybe a context is a sentence. You look at every sentence, and you look how often do these two words in, let's say, stamped forms, so you don't make a distinction maybe between whatever tenses and gender and maybe whatever. You look at when do these two words appear in the same context, how often, right? And so you write down numbers, right? This is whatever, 10 to the 7, this is 0, whatever these numbers are, right? Now you have a matrix, and so this is clearly meaningful, right? If two things appear, two concepts, two words appear very often together, then there's some kind of relationship that you have between there, right? And once you have this, you apply the matrix factorization exactly in the, like what I wrote down here, except don't do it with just, with matrices of rank 1. Do it with slightly larger matrices, right? So do it with maybe something that has k here, right? This k has nothing to do with the previous k that I had, right? So this is k. And now what you get, right, if you can do this, you will get for every word vectors of length k, right? And the hope is that they have some meaning. And people have done this, and you get, Martin will can give you amazing demos, okay? I can only tell you, so, okay, it's not very amazing, but you can find very, very nice things. Like you can find things, maybe I even showed it to you in the first lecture, right? You can find things like whatever. You have maybe you have here countries, okay? Whatever, you have maybe here Great Britain, and maybe you have France, right? And then maybe you have Switzerland, okay, blah, blah, blah. And then maybe here you have whatever, you have London, right? And Paris, and you have Bern, right? And you will find that now each of them corresponds, each of them is a vector, right? So these are points in a space. And what you will find is not necessarily, maybe you find also that some of them are closely related, but what's even nicer is that you will find is that the vectors, namely how far you go from, or the vector that brings you from, let's say, Great Britain to London, okay, if you take that vector and you add it to the vector to the point France, you get very close to Paris. Okay, so you find that there's actually a lot, and there are many other examples, and he'll show you many more. You find that there's a lot of the semantics in there is preserved in this representation. Okay, I think that's, if you think about it, if you haven't seen this, that's really quite amazing. So you can actually, you can kind of do calculus, right? I don't know if you can do recipes or whatever, okay? Give me some recipe, and then you add it, whatever. Okay, so you can actually do calculus with these things. And clearly, once you have a representation that's meaningful, it's clear that this will be much easier to learn task, right? So this is just now to represent these words, and now on top, you want to learn something, right? We'll get back to it. Good, so this was matrix factorization. So that's clearly has something to do with feature learning, right? What we're learning is we're learning what's important, right? We're learning, you can think of this now as the features, right? So we're learning what these features are that are important, right? Or these numbers that we have features. So it selects automatically for you what are the features, right? We didn't construct these features. We didn't construct these vectors, but this came out from some unsupervised learning task, right? All we gave it is just the words themselves, and we gave it a huge corpus, and implicitly it generated for us the right features. Okay, so this is not the only way how you can learn nice features. And I know you're very eager to learn, but unfortunately we have to take a break, and I can only tell you afterwards. Okay, good.